Okay, I guess we will just continue. So, next I'd like to talk about something known as KL-divergence. And actually, it's also known as the relative entropy. So I guess, but I think like KL-divergence, the name is more common. And KL is a I don't know how to pronounce the name. It's a Kohlberg Lieber divergence, something like. I don't know. My spelling probably is not correct. Anyway, so but let's just call it KL divergence. KL divergence is basically a way to measure how different between two distributions. For example, I have two distributions like px and qx. So I have, for example, like I have, let's say, a continuous. Of course, KL-divergence again, like many of these information theory concepts, like you can apply to both kind of discrete and continuous random variables, but the equation will be slightly differ. I mean, actually, in this case, the equations are almost identical. Like many cases, it's just like the summation will be replaced by integral. And let's say I have like two distributions, like this is like px, and then like another distribution, let's say qx here. So I want to measure like how different between these two distributions. So some possible measure can be like just the square difference and so on. But KL-divergence is like kind of very convenient because it's very easy to manipulate. So therefore, it's one of the most commonly used choice to measure like the difference between two distributions. So basically, the definition is like that. So let me write like KL-divergence between like x, p, and q as this way. I mean, it's basically defined as. So this is my define. I write it as triangular equal as for summing over all the. Here I'm assuming the distribution is discrete, so therefore it's a sum. If it's a continuous, then it will be like an integral here. Px log px qx. So one thing you want to put extra attention here once you see this definition is that like the definition by itself apparently is not symmetric. So therefore, like, when I say the KL-divergence between px and qx is actually different from like qx and px. I mean, this does not equal to KL-qx px because this is actually equal to this sum over x qx log qx px. So strictly speaking, it's not exactly a kind of measure. So therefore, people call it a divergence. Like it's not a measure of distance or something like that. Because if you measure, when you say like or I should say a metric, like in mathematics, like when you say a metric to measure something, like the metric is supposed to be symmetric. In this case, it's not. So it's not that defined like that. But still, like this is very convenient because as you can see, if I have two distributions as identical, so what I mean is if I compare KL-divergence between px and px is exactly equal to 0. So it's very nice. So that's something I can't expect, right? So if I'm measuring the distance between itself, it should be 0. And of course, this is apparent. I mean, can be easily verified as if px, I mean both px and qx is the same, then like this will just cancel. It will be just log 1. Log 1 is just 0, right? So it's just basically 0 everywhere. And also like for this to have some kind of distance meaning, then I kind of hope that like if KL, if like P is not equal to Q, if the two distribution is not the same, then I should have like Px, Qx is kind of like bigger than 0, something like positive. That's what I hope for. Let's kind of show this. Let's show this one. I need to again like create a new page here. New page after. So let's see, like KL-divergence of Px, Qx. So again, like from the definition is equal to sum over x. Let's ignore the part here. Px log Px over Qx. So I can flip the sign here, become Px. Just kind of inverse the fraction here. So into like Qx over Px. So, but then like writing this allow us to do something like let's see, here I use the unit bits here, right? So it will be let me change this log into a lateral log. So if I consider lateral log instead, this will be just Qx Px divided by constant like Px over log 2 here. It becomes like that. Like if you're already using lateral log, for example, you consider lat, then we don't have a factor here. But in any case, it doesn't affect the result. But just think of the lateral log of a fraction here, or lateral log of some x here. We have an interesting property that like log x as a function would be something like that, and consider like another kind of like this is y equal to log x basically. This is y equal to lateral log of x. This is x, y here. Now let's consider also the straight line y equal to x minus 1. I'll claim that the straight line is above this, and I'm actually let's see, will be above this. I'm exactly hit here. Let's see, where should it hit? I think this is 1 here probably. It's not in scale. It will hit this line exactly at y x equal to 1. So it's kind of apparent here, right? When x equal to 1, they will hit each other, because when x equal to 1, y equal to log x is just y equal to 0, x is equal to 1, right? And also for this, okay, like this. This is kind of even make me confusing. Confused. Let me just remove here, and let's use a different color. Okay, this is a y equal to x minus 1, right? What I'm claiming like this y equal to x minus 1 is above this this curve y equal to log x here, and it's exactly hitting one another when x is equal to 1. So for that part, we can very easily verify that way. Just substitute x equal to 1, both of them equal to 0. So so therefore the 0 is here. This is the origin 0 here. So maybe I just make it less confusing. So because this is supposed to be 0 here. Probably it's better, like this x, this is 1 here, minus 1, this is both of them 0, and for all the other places, like y, this line here is above this one. It's kind of like very easy to show. I don't want to spend time on that because this curve like is convex, right? So therefore actually we mentioned that the property of convex is like we draw a line somewhere, like if I draw a line like hitting these 2 points here, then every point in this line will be like below, sorry, like this is actually concave, like will be below this curve here. But also like you can also see like for a function to be concave, basically the slope will be continuously decreasing if like the function is 1D. If we consider just the 1D special case. So the derivative is continuously decreasing, and then of course if you hit at this point here, basically tangential at this point here, there's no way that it will going to hit this going to hit this line again. So basically if you want to show like this curve here is below this line, what we need to show is just like it's hitting this line here at this point, like overlap with this line here at the point like x equal to 1, but at the same time it's tangential at this point, so therefore like the slope at x equal to 1 should be identical. So this is also very easy to verify, right? The slope for this line here is just equal to 1 here. If I take the derivative here is 1. If I take the derivative here, is equal to 1 over x, right? And also when x is equal to 1, it's also equal to 1. So therefore both the slope and the point overlap here, so it's tangential to this here, so therefore like this line has to be above this curve. So anyway, like that we have, so therefore we basically have, our conclusion is like we have an inequality from this geographic description here is like log x should be less than equal to x minus 1, right? Something like that. And now let's see, like log x is less than equal to x minus 1, so therefore this is less than equal to sum over px log 2, x minus 1 is qx over px minus 1, right? Now then we can expand that, then this will become like qx over log 2 minus let's see, px over log 2, right? Then of course like both qx and px are distribution, they sum up to 1, so therefore like they will be just cancel each other, so therefore this is equal to 0. Wait a sec, I have some problem with the sign here. Oh, okay, yeah, I have a minus sign here, therefore like this should be, so here is saying like log x is less than equal to x minus 1, right? So therefore like minus log x is bigger than equal to minus x minus 1. So this is like the sign should be flipped. So therefore like I have like KL-divergence for any two distribution has to be bigger than equal to 0. Yeah. So this shows that like KL-divergence has to be positive. And for continuous case, I just basically everything will be replaced by integral, right? This will be just integral integral. So everything will still hold, right? So when at the very last equation here, last line here, that we have integral over the PDF. Again, integrating over the PDF will be just resulting 1 here. So again, it's 1 minus 1, we got cancelled, and again, it's like bigger than includes 0. So therefore, either case, we have the KL-divergence is a positive. Now, why we introduce KL-divergence? Remember that just before that, we mentioned that we want to find an upper bound for the differential entropy, and we say that we want to introduce some constraint there. So basically, we go back to a question that if we have when the variable x is continuous, and let's say we have some constraint on the variance, have a variance sigma square, x and sigma square, then we claim just a moment ago that before the break, that the maximum entropy for x here would be when x have a Gaussian distribution. So therefore we'll have this will be less than equal to log 2 pi e sigma square, something like that. That is basically the entropy of a Gaussian distribution with variance sigma square. So, but this was just a claim earlier. We didn't show why Gaussian will have the maximum entropy for the fixed variance. So now we're going to show that. So basically, here we'll show the general case. We'll show that not just for the 1D Gaussian case, that Gaussian will have the largest entropy among all distribution have the same variance, but also for, let's say, vector Gaussian, for multivariate Gaussian, and for a fixed, now in this case, because we have a multivariate Gaussian, what we have to fix is the covariance matrix. And let's say we fix the covariance matrix, then Gaussian again will be the distribution with the largest differential entropy for the fixed covariance matrix. So to show that, let's say let's write the PDF of the Gaussian distribution. So basically, let me denote the PDF as this one. So again, the mean is not important, right? So I will just assume 0 mean here, because the mean will not affect the amount of the entropy of a distribution or a random variable. So let's say this is basically the PDF of the Gaussian distribution, right? So I just use a shorthand notation like that. I'll just do an even further shorthand notation, as I just find x here is the PDF of Gaussian distribution. If you remember, this basically is something have a form some scalar factor m exponential, something like x inverse transpose x, something like that. Oh, wait a second. X transpose x 1/2, something like this. Yeah, but it doesn't matter. I at this moment I don't want to spell this out. I just shorthand this as this one. Now let's consider any distribution f. So this is a distribution of x, also have covariance matrix sigma. So I might have a distribution 5. This one is Gaussian again. This is Gaussian or normal. No, normal. Gaussian or normal. and this is any other distribution, let's say. And again, okay, so of course a distribution over x, and covariance matrix is sigma. Now let's consider the KL-divergence between f and phi here. Of course, we know that this has to be bigger than or equal to 0. That's what we just showed earlier. And by definition, this is equal to xfx log fx phi x here. And now let's just write this down, and then this I can expand that. Fx log fx dx minus x fx. I'll just keep some of this bar here. I mean, this is like x is vector, but it doesn't matter. Log phi x, let's say dx here. Now, of course, the first term here is just the minus entropy, right, of x. There's nothing special, or like yeah, the minus entropy, or like I probably want to use a different notation because it can be confusing. I have x, like both of them are x, right? But after all, you remember that like the entropy should depend on the distribution of x rather than x itself. So here I probably want to write h of f to avoid kind of confusion. So like let's say something like h of f here. And for the second term here, what I want to claim is that okay, if you have the if I look at this is the PDF of the phi x, right? And then if I let's see, I may need to go a little bit farther. Let's see, this exponential minus x transpose sigma x over 2, and what else here? This is 2 pi 2 pi sigma square, right? Determine sigma. I forgot the scaling factor here, so it doesn't matter actually. It doesn't matter because what I want to say is that like if you look at this here, if I take the log value of this guy here, this distribution here, what I want to say, it only depends on sigma, right? What I want to say is that basically the PDF of the Gaussian distribution, I guess one of you guys I copied it badly. Let me see. Anyway, Benny, you may want to like mute the mic, or actually I can do it for you. Yeah. So so what I want to say, okay, this is and let me come back to here. So phi x here, what I want to emphasize, phi x is the PDF of the Gaussian distribution, right? And the PDF of the Gaussian distribution only depends on the mean and the variance. And of course here I assume zero means, so therefore like only depends on the variance here, the covariance here. So therefore like remember like what's common for phi and f here is like they have the same covariance here, right? Covariance is the same. So therefore, like since log phi x here, this function here only depends on the covariance. I can claim that like if I change this average, I mean basically I'm doing an expectation of log phi x over the distribution of f, right? But this will be the same as I find x log phi x, right? Okay, I'm not sure I explained it clearly, but do you all agree with me? So basically, because both of these two distributions have the same covariance, right? And this log sigma here only depends on the covariance. Then of course these two guys is identical, right? Okay, I may want to stop here, but do you guys all agree with that? Like basically, maybe I should unmute some of you guys. So hearing none, then I assume that you guys are all happy with that. So then so therefore like I can write this instead. So of course if this guy is replaced by this, what is this? This is simply equal to the entropy of phi, right? So it's just hf minus h phi, right? Okay, this is actually plus h phi, right? And of course, we have the other side is like bigger than equal to 0, so therefore like h phi is bigger than equal to hf. So this is very nice because you see like this holds for basically the Gaussian, I mean the vector case. So of course scalar case is just a special case. So for any dimension, Gaussian basically have the highest entropy given the same covariance. And actually this kind of like give a hint why we have the central limit theorem, because when you mix the independent noise together, it's just like you increase the entropy, right? I mean, like, of course, it's not a proof, but it's give you a little bit intuition. Like when you're mixing things together, your entropy tends to increase, and it increases to a way that how you are able to increase that, I don't know whether it's a good argument or not, but how you're going to increase increase that. One way is like if you become more and more Gaussian, right? Oh, okay. I know it's a very hand-waving argument, but it's like just maybe just something like can elaborate more, or like someone may be able to prove it along that way. But so anyway, like just remember this result. Actually, this is a very nice result that that also give another reason why people like to use Gaussian to do analysis, because after all, like because of this result, even though your approximation may not be accurate because your distribution is not Gaussian, but often like it will end up like it will give you a bound or something, right? Because Gaussian will be the case give the largest entropy. So with that, like oftentimes it will give you like some kind of worst case or like the best case scenario. So it will give you a bound like when you study Gaussian case. So and
Dr. Cheng?
Yes.
So why you make a similarity between the Gaussian in the P in here with the F? I still don't understand.
Oh, okay. F is not a Gaussian. F is any other distribution. You want to say like for any other distribution? Yes.
In the second integral, that you create that the Gaussian is similar to the F in.
You mean this one is equal to this one, is that?
Yeah, that's right.
Yes, actually, like in my slide, I elaborate much more. Maybe I try to elaborate. So like I can, for example, consider this like find x log find x, basically the lower term here, dx, this guy here. So if I expand that, like what is find x here? This thing here is basically it'll be like actually this was wrong. It should be determinant 2 pi sigma. So it's okay. So this will be equal to like phi x log the PDF here will be log this term here will be minus log something, minus log determinant 2 pi sigma, and log of this guy will be like minus 1/2 x transpose sigma x over 2, something like that. Okay, that should be an inverse here.
Yeah, that's right.
Yes. Now let me write this. Let me expand this sum here. This is actually a sum, right? Because this is a actually x transpose is a row vector multiplied by this is a matrix sigma inverse multiplied by x is a column vector, so it's actually a matrix multiplication, kind of like a vector multiplied by matrix multiplied by column vector again. So then it's actually this is equal to sum over imj xi, the sigma inverse. So these two look too similar, I'm sorry about that. ij xj, something like that. I'm just expanding this guy here. Do I write 2? Okay, yeah. And 1/2 I can put it out here. Just and this, of course, like this is now after the summation. These are just numbers, right? These are numbers. I can put them together here. Xi, xj, put them together, and I have like sigma inverse ij sum over ij 1/2 inverse. So I still have this log whatever something dx find x here, right? Now the first term is basically just a constant, right? So yeah. Phi is a distribution. So what I mean is I replace phi x by fx. It doesn't change anything for the first term, right? Because both of them is just equal to this constant here. In either case, I can pull this outside. And for the second term here, I can pull the integral all the way inside this one, right? And I can have like basically integral phi x, and I have xi, xj here, and then I have this sigma inverse ij sum over ij dx here. Now, but what is this thing here? This one here is actually just the covariance between like xi and xj, right? Yes, do we call it covariance? I'm thinking like how do we call that? Like Like okay. Anyway, let me just wait. This is actually just like sigma ij. Benny, do you follow me? Like here?
That sigma ij from the Gaussian. Does it mean that the same with the previous one in here?
Oh, I mean like when from this step, okay, from this step to this step here, my integral just pull inside into here. Then I'm actually doing a integral of just this two term here because this can be considered just constant, right? It doesn't depend on x, so I just go all the way inside here. But if I look at the integral of this guy here,
This covariance.
yeah, this is just the covariance, and the covariance for like the I component and j component is actually just the sigma, the ij component of the sigma, the covariance matrix. So therefore, this is actually just sigma ij.
Yeah, that's right.
Yes, but then of course like this is also just equal to f x xi xj, right? dx.
Yeah, that's right.
Yeah, because they have the same covariance, right? So therefore, you can see like here, for both of these terms here, I can swap this phi x as fx. It doesn't change anything. Just that, therefore, like eventually, I also have like the whole thing. I can just switch this phi x into fx and doesn't change anything. So therefore, have this term here. So from kind of fx log phi x become like phi x log phi x.
Yeah, that is doesn't change anything, but they change anything because in the first there is log determinant, square root determinant that can make a change.
Oh, you mean this one?
Yeah, that's one.
Oh, this is a constant. It does not depend on x. So therefore, I will put.
And that equation come from the Gaussian. So, yeah.
Oh, but if like let's say I swap this finance with fx, I integrate this guy like with a constant.
Yeah.
Dx is still equal to that constant, right?
Yeah,
because this
right.
is also a distribution.
Yeah, that's right. But that is in the Gaussian.
Oh, this one has to be Gaussian, yes. This log finance has to be Gaussian. This one has to be Gaussian. But if this is Gaussian, then like it doesn't matter like whether I'm taking fh over like phi x or fx. So therefore, like if I'm going back to the earlier, I have this guy written at this one way. Then the first term is just href. The second term is this guy way. But then it doesn't matter like this, because this part is a Gaussian. Then I can really change this fx into phi x with the same covariance and doesn't change anything. So therefore, the second term is actually just equal to h phi. Yeah. So yes, that okay. Thank you for the question. So so therefore we have for a property for kind of KL-divergence that like Gaussian have the highest differential entropy for a fixed covariance. So actually I just still taping. I forgot to stop it. But anyway, now let's see. Let me create another page first. Let's give an application example for the KL-divergence. This side from economics. I guess you may have heard of that before. Like I don't know how to pronounce it exactly. I think it's Thiel index or something like that. Thiel. It's very hard for me to pronounce th. So basically, this is an index to measure like inequalities among a society. So you can have different groups in a society. Let's say like you have different groups there. Like I don't know. For example, like you can think of like simply maybe like for different states here, right? I have like different. This can be U.S. Like let's say I have like 50 states here. Like this is like just different states, and each state will have like different populations, right? So then therefore like I will have a population for the state of US. So like I have a PDF of the population distribution for the population, I say. I'm thinking how to pronounce spell population. I think something like that. So then maybe like I have 50 states here. So California is pretty high, and then maybe like New York pretty high, maybe Texas and stuff like that, right? Have a distribution. This maybe California, this is New York, and so on, right? Now I can also do the distribution in terms of wealth, right? So how much each of them own. So and of course I can make a distribution to kind of like just normalize into one. So this is like add them all together. So we added all to one, and this is again like another distribution. Maybe California is a pretty rich. Actually, I think that the highest one maybe is probably it's not California. I don't know. Probably upstate in the East Coast, and maybe Oregon or something like some of those. So anyway, and then we have Oklahoma is probably in the middle, pretty poor, like Mississippi and so on. Like, and then you have another distribution, right? Maybe CA is like that. New York, I don't know whether it's richer and poor. Probably it's a little bit poor. Texas is probably way more poor. I don't know, something like that. So and then like okay, how do you measure inequality? A suggestion? Any suggestion? Given these two distributions. Let's say this is the distribution in terms of wealth, is a distribution of P, called P, and this distribution called Q here is the population distribution.
Measure what?
Measure inequality. Society, like income inequality or like the wealth inequality. This is the Thiel index to measure this income wealth inequality. Or you can do the same thing for income as well, of course. If if this distribution is income.
By using KL.
Yeah, exactly. You can use in KL. Actually, that's exactly how this Thiel index is defined. It's just like so. If it's like kind of like if you expect like stuff is kind of equal, like people equal. So if you have the population is so much, then the total wealth is also like contributed approximately the same amount, right? Same fashion in terms of the whole size of the country, right? So basically define the Thiel index as just simply like KL-divergence between P and Q. Don't ask me why not Q and P. I don't know. This is but somehow they pick like P and Q, and you can actually that's probably like good reason why it's like PQ instead of QP, but because but anyway, I would let you think about that. So so let's give an example for this Thiel index here. Like let's say if I apply to a group of n individuals. So in this case, I will have, you can think of like n groups here, right? N groups here, like each group will have just population of 1, right? And then like, let's say, just look at 2 simple cases. Let's say if like everyone have the same wealth, so what was the Thiel index? Any quick guess here?
Will be infinity.
No, actually, look at PMQ here. What was PMQ in this case? Like if everyone has same wealth. First of all, Q is like because like we will just have a uniform distribution. Right? We're saying that n individual we compute like for each, assuming each individual is a group, so all of them will be like have like one person in the group, so it would be just a uniform distribution with like n values here, right? That would be Q, basically. The height is basically just 1 over n. And how about P?
P is wealth.
Yes, P is wealth.
So if everyone the same wealth, so it's same with what is it?
Q.
Same with Q.
Yes, it's also uniform, right? So then like wealth is also uniform. Then okay, then I don't need to draw it. So in that case, then both of the distribution will be identical, right? So therefore, like when you have like identical distribution, P and Q is the same, then the KL-divergence is just 0, right? So that's why like this is a measure of inequality. So it's reasonable, right? Everyone have the same wealth, so the index should be 0. It's a very ideal case. There's no inequality at all. Everyone have this. This is basically it's a real communist or socialist, not a fake one. So then if one of them, let's say like let's look at another example, like extreme second case. Let's say also I have n individual, but one of them is more than Bill Gates. It's like own everything. Owns everything. So again, I was the Thiel index. So in this case, Q is still the same, but then like
will be more than 0 then.
oh yes. Let's go through that. Like then, but in this case, like Q is still the same, but P is like just a delta function. Right? I have one of them own everything. There's 1, and the rest is just equal to 0. So then I compute the KL PQ here. Actually, that give yeah, you see why we want to compute KL PQ instead of KL QP. Probably in this case, simplify the things a bit. So it's like equal to sum over pi log pi over qi, right? But this sum here actually will have only, let's say, without loss of generality, let's say I have the first one owns everything, the first guy owns everything, so it's just equal to 1, just have one term here, it's just equal to log 1 over q1, something like, right? Because I only P1 is equal to 1, the rest is just equal to 0. And of course, like Q1 is just equal to 1 over n, right? So therefore, it's just log n. So that's an example, a very simple application example of KL-divergence. So any question here? And if not, let me give another example again. Let's look at something that probably more relevant to us. So let's say we in sorry, I just need some water. So let's see an application in machine learning. So okay, like how fancy word machine learning is just like, you know, you have some patterns or like something, and from that, like you want to, from the data, to learn something. Like for example, like a very typical example of machine learning would be like a classification problem that that you have some input data, and based on the data you want to classify some result. And let's give an example. For example, like I have some input data. I didn't specify what are the input data, but let's say I have a classification system trying to go through some record of some person, individual, and based on that, like the system will determine like how what is a political like inclination of that individual, whether he is likely to be a Democrat or Republican, like, or the others. And so let's say I have some in the data. After I prepare some training data, or like prepare some data that I have several individuals that test with like 3 different individuals, I say, and for the first guy here, for the system, basically it detected like the first guy will have like probability that like okay, I need to specify what this number means. This number means, wait a sec. Okay, yeah, okay, the first one is I identify as other. The second one identify as a Republican, and the third one identify as Democrat. So basically here it's saying, okay, after looking at some data, and the system determined that like from the data that I have like 40% of confidence that like the individual is a Democrat, and then have like 30% is a Republican and 30% of the other candidates, or like my Green Party or whatever. And we have the actual result, the ground truth here. This target is ground truth here. That basically the reality. So maybe that guy is really a Democrat. So it's like actually 100%. So therefore, like for the ground truth, if we specify like it's like with 100% confidence he's actually a Democrat, let's say, and then again, maybe I have another record. I have result like 0.3 0.3, sorry, 0.3, 0.4, 0.3, and this is a 0, 1, 0, and then this guy have some other data that like 0.1, 0.2, 0.7, 1, 0, 0. Let's say this is the result. Okay, from here you can say, okay, you can see for the first record, the system like make a correct prediction, right? Because it say like most likely is a Democrat, indeed is a Democrat, and the second record is also make a correct prediction, and like also now in this case the most likely party will be like Republican, and also the ground truth is a Republican, and then for the third one, it predict Democrat, but actually the ground truth saying that it's not Democrat, but maybe some other party. So so this one is incorrect. So I have some correct result. This is incorrect result. So let's say this is a system A. This is prediction from system A. Then I have a system B. Basically, for the same record, but the computer result for system B will be like, this is system B. Let's say 0.1, 0.2, 0.7, and then 0.1, 0.7, 0.2, and 0.3, 0.4, 0.3. So again, the same record. The ground truth is still like this. It's like 0.001, 1010, and 100. So if you look at this case, again, like for the first record, it predicted correctly, right? So it's like this one is also correct. The second record is also like predicted correctly, and the third record, like this system B determined that guy is supposed to be, predict it to be a Republican, but actually is actually independent or like other. So so it's incorrect. So now the question is like, I basically, one of the interesting question in machine learning is like you have several systems like with some training data of the result, like this is first system, system A have estimated result like this, and I also have ground truth, and system B also estimated the result like this and have ground truth. Now I want to evaluate the performance of each of these systems. Like we just want to determine which system is better. So I guess it's very apparent that in this situation, which one is better? So anyone is still here?
System B, I think.
Yeah, system B should be better, right? But like if you, in terms of like simply counting the number of like correct prediction or incorrect prediction, you cannot judge which one is better, right? So it's not it's not a good measure to just use the number of incorrect or correct result to judge which system is better. So again, like this, the KL-divergence can come into use. So how are you going to use it? So again, you look at this, is very apparent, right? If I have like prediction like this and a ground truth like this, I can think of like each of this is basically a distribution, right? Again, right? For a particular record here, let's say I have a record, one record here. The predicted result, or like the predicted distribution. I already say it's distribution. It's a distribution, right? So and also for the target, like if I write it this way, it's also like a distribution, right? But it's like kind of a delta distribution, because like for the ground truth we know exactly whether it's a Democrat, like Republican, or independent. So, but ideally, if we make the 100% like call prediction, we hope that this two distribution, or like maybe like I should put it this way, like the prediction will be better if like these two distributions is more similar, right? So ideally, we want to have these two distributions as close as possible, and we can use KL-divergence to compute that way. So we can compute, let's say, the KL-divergence between the distribution, like of the target one, and the distribution of the computed one, the predicted one. And then in this case, I can write this as P target
log.
Yes, log P target. I'm thinking that I probably want to put some sum over different classes, where I have different classes. I say this is classes here, this classes here. In this case would be like Democrat, Republican, individual, or let's say this P computed C, let's say something like this. And then I can expand this KL-divergence as a sum over P T C log. I don't have a minus sign here. P T C minus P T C log P C C, something like that. Now this target distribution, we have no control with that, way. So therefore, like this we don't care exactly, right? This is something we don't actually care. And of course, this that we don't care is actually the minus entropy of the target distribution. But as I said, like we don't actually care. Like in terms of like evaluating our system, it's not relevant. Only the second term is relevant, and this is actually the second term that appear often in machine learning literature, and it was known as the cross-entropy. And in practice, people will compute the cross-entropy. Like this is sometimes known as a cross-entropy loss function. So to evaluate the system, like we instead of computing like how many correct or incorrect prediction, we'll compute the average cross-entropy. Basically, for each record, we can compute the cross-entropy, right? And then we just average that out. So, and we want the cross-entropy to be as small. In this case, as small as possible. So that like your system will be if of course if it's equal to 0, basically your prediction will be ideal. So there's another example. Like any question here for
Jack?
Yes.
So how to calculate the probability of target in here? We don't have.
Oh no, we have actually, but it's like kind of like trivial target because we have the ground truth, right? So here we assume we know the ground truth. Basically, we have the first record, second record, third record. We know that guy is actually is a Democrat, Republican, Independent, let's say. So because let's say for the first guy is a Democrat, then the distribution will be just like this 001.
So it means the probability of the target is 001.
Yes. The distribution is 001 for that record. So therefore, like basically probability. Let's say this guy is just John, whatever. This guy is John. So we have the probability John is equal to a Democrat is 1, something like that. Okay. And John is a Republican, the probability is just equal to 0. And John probability is independent is equal to 0, something like that.
Oh yeah. Okay.
Yes,
Yeah,
yes.
I know.
And this is a distribution, so therefore you can compute the KL divergence of your. Also, you have a predicted distribution like this way, for example. Then you compute the KL divergence between these two distributions.
Okay.
Yes.
Understand.
So see, I have one more example whether so let's look at another example, like again some use for like KL-divergence. So here is an example for text processing. So it's very common that in text processing we want to say we have two documents D1, D2. We want to see like how different, how similar these two documents. So we just want to kind of like maybe like put similar document together. Think of like you're having a search engine, right? So and you have one document, want to find similar documents. Right, we have this document one about like, I don't know, President Trump have a new bill for something, and then like from that document, like we want to kind of like find all the similar documents. So then of course, like first thing first, we need to find a similar measure, right? How do we? Define a similar measure for that. So I think like, so this the idea is, the main idea again, like if we want to use KL-divergence, as you see the basically the how this all similar ideas is like we try to convert things into like distributions, and then like we can measure the distribution between these two. For example, if we can kind of generate a distribution to represent a document, then we can just compare the distribution between these two documents, and then like if the two distributions are close to each other, then the two documents are more similar. So one representation like people use is like using so-called the back of words hard for me to pronounce. So so basically, a very simple idea, if you have a document, for example, like I say like a very simple, like let's say if I have a document, it is an expensive bag, let's say, just like this, like I have, okay. Maybe I need to say it's more, is and the bag is expensive. So it's very silly, right? But anyway, just give an example. This is a document. And now maybe I have a document. This is a document 1. I can document 2 is like it is an expensive watch and watch out, let's say, whatever. So now what back of word does is basically it trying to generate a distribution of document based on the number of occurrence of each of the words in the documents. So, for example, like for D1, I look at all the words here. Right, I have words like it, I have is, I have and, I have expansive, I have back, and I have and, the, something like that. Now, number of occurrence like for each of these character, sorry, not character, each of these words here, it occur one times, is occur 2 times here, right? And occur 1 times here, expansive occur 2 times here, back occur like 2 times here, and occurs 1 time here, and third occurs 1 time here. And in the second document here, I can do the same thing here. Let's have like it is and expansive. Let's see, I might have character and I have like watch hour, and it occur 1 time, is occur 1 time, and 1 time, expansive 1 time, and occur 1 time, watch occur 2 times, hour occur 1 times, right? Something like that. Now there's some characters like that, some words only occur like in document 1 and some only occur in document 2, but let's make an kind of like a union of these 2 sets here, and let's also count the characters, I mean the words occur in either of these documents. So I can say document 1 have a distribution like this way in terms of all these words here, like it is an expensive word and watch and the watch hour or whatever like this. And document 2 I have like a distribution of word like this. Of course I supposed to normalize that. Let's see if I try to normalize that. This is like 5, this is 10, right? 10 word here. So I should divide it by 10. This is 1/5 here. Okay, let's just put 210 anyway. Divide by 10. I have distribution like that. The second one, I have 8 word here, divided by 8, right? Now, as you can see then now, because I have distribution, right, for these 2 documents, just in terms of the number of colons of the words, we can compute the KL-divergence between them. Wait a sec. Yeah, we can use KL-divergence to compute the distance between 2 documents like this way. Any question? I have more elaboration in the slides actually. I mean, it's based on cross-entropy. But I probably don't have enough time to go through that now, so maybe I will just stop here today. We'll come back next week. I probably will. Oh, actually, you guys are okay for me to just do like this way. I guess I will just kind of make it kind of a kind of online course from now on. Then I will just teach from whatever wherever I am, I guess. So but if you guys want to meet sometime, then maybe just let me know. And again, I will leave some homework assignment today, or later today, or maybe tomorrow. And again, it'll be I will. I mean, I will put on both Canvas and also Canvas. I will put a link there, but most likely the homework will appear on my website. So then, but please submit your homework to Canvas. So anyway, I'll talk to you guys next week then. So okay. So I stop the